Hello everyone. So in this lecture we will be discussing about the min coins problem. And what does this problem ask us to do is, this problem asks that you're given an array n and an amount x, and where array n contains the denominations, and you need to find the minimum number of coins in which you can make the change or the amount. Again, you have infinite supply of each and every denomination, so there is no need to worry about the supply of the denominations. Now in the first example, what do we see is that we are given an array of denominations 1, 2 and 3, and you need to make an amount of 4. So what are the minimum number of coins with which we can make it? We can again make it with the help of 1 and 3 or 2 2's. So the minimum number of coins that would be needed is 2. So our function should return 2 in this case. In the second example, if we see what are the denominations we have 1, 5, 6 and 8, and the amount which we want to make is 11. So what are the minimum number of coins which we need to make 11 out of the given denominations? It would be again 2. We would pick a 5 and a 6. So before approaching this problem, when I first approached this problem, what I had was in my mind that I can solve it with the help of greedy approach. And why greedy? Look, because you are given an amount x, if you just deduct the maximum denomination you would be having in your hand, so what you would be left with? You would be left with the minimum number of amount, and hence the minimum you have got would need minimum number of coins. But that's not the case always. Now it might help you in the first example where you just deduct 3 from 4. So what are you left with? You are left with only 1, and that 1 you can just make out by a single coin of one denomination. So you have in this case 1 and 3, which are the minimum number of coins needed. But if we take the second example, what do we have over here? We need to make an amount of 11. And what is the maximum denomination which I have? I have a maximum denomination of 8. So I just delete that amount from 11. So what would I be left with? I would be left with 3. And with the denominations array, what are the minimum number of coins with which I can make 3? I need to take at least 3 ones. So in how did I make 11 then? I just took 3 ones and an 8. So how many coins did I used over here? I used 4 coins, but they are not the minimum. Hence, a greedy approach wouldn't be able to solve this problem in each and every scenario, and it won't give us the most optimal solution. So how do we do it then? We will first use recursion to check that whether do we have our overlapping subproblems and does it have an optimal substructure. And if it has both of these properties, then we will try to solve it with the help of dynamic programming. Again, we will make use of the algorithm we have previously used in coin change problem and in subset sum problem. So give it a try, pause the video and then come back to it, because I will be starting with the explanation now. Now coming on to the explanation, what do we have over here? We are given a denomination array of 1, 2, 3, and we need to make an amount of 4. So what do we have? We have some base cases and we have a recurrence relation over here. So, but why are we returning all this? 0, int max minus 1, int max minus 1. I think it would be far more better if I just go to the recursive tree and just start discussing all these things over there only. Now coming on to the recursive tree, what do we have over here? We do have a function minCoin. This is the function which would be returning you the minimum number of coins, which would be used to make this amount from this denomination array. What is this ARR? This is again a reference or a pointer to the denomination array. What is this 3? This is the total number of elements you have in the denomination array. This 4 signifies the total amount you want to make. And what is this 0? This 0 signifies I am currently present at which index. So if this says 0, so I am sitting at my first index. Now what we had in our earlier problems, what we used to do, we just considered each and every element and we branched out. And what was the method of branching? We just considered that element present at the index, and in other branch I wouldn't be considering the same element. So in this case, if I consider this one, or I consider the element present at this index 0, so what do I have over here? I have my array 330 plus 1. Now what is this 3? This 3 says, just tell me that I have deducted a 1 from here by using a coin. So what does this subproblem say? This subproblem says, just tell me I am sitting at index 0, starting from this index to the end of the array, what are the minimum number of coins I need to make to have a 3? Again, what does this subproblem say? This subproblem says, look, I am sitting at index 0. Just tell me, starting from this index till the end of the array, what are the minimum number of coins which are needed to make 3 out of it? And why did I add plus 1 over here? I added plus 1 because I used up a coin in this case. Look, I had an initial amount of 4. I used up this one. So whatever might be the case of this thing, even if it's 0, but at least I would have used one coin of this one or the element present in this index, and hence I would be adding 1 over here. And what does this min coin problem specify? This subproblem specify, just tell me, starting from index 1 till the end of the array, in what are the minimum number of coins with which we can with which I can make an amount of 4. Or this subproblem says this thing, I am present at element 1, just tell me this thing, with the help of a 2 and a 3, what are the minimum number of coins needed to make 4? This problem specifies this. And what does this problem specify? This problem specify, I have a 1, 2 and 3, just tell me what are the minimum number of coins needed to make a 3 over here. So again, I am present at index 0, so I will be branching out. If I include 1 or include the element present in index, include the element present at index 0, and I would not be including element present in index 0. So what if I include it? Then what would I be left with? I would be left with 2, 0. And what does this 0 specify? This 0 again specifies that, okay, just tell me, starting from this 0 index till the end of the array, what are the minimum number of coins needed to make a 2? And what is this 2? 2 is the leftover sum from this 4. This 4 was the initial amount. I just reduced 1 from it because I used a coin, and hence I added 1 over here. Again, after receiving that 3, I again use this one. That's why I'm adding again 1 over here, so that I would be left with an amount of 2. What does this subproblem say? This subproblem says that currently I am sitting at index 1. Just tell me, from this index till the end of the array, what are the minimum number of coins with which I can make 3? The problem says this thing. I am sitting at index 1. I am sitting at index 1. Just tell me, starting from this index till the end of the array, starting from this index till the end of the array, what are the minimum number of coins which I need to make for 3? For 3. So for an amount of 3, what are the minimum number of coins needed in case I have these two denominations? This subproblem states that. Again, I will be branching out with in this subproblem. Again, what I would be doing is I would be including my element present at this index, and I would not be including my element present at this index. So if I include it, I would be left with a 1, because what is the element present at index 0? It's 1 again. So I would be subtracting that coin or subtracting that denomination from my leftover amount. So if I subtract it, what would I be left with? I would be left with a 1. So min coin 1, 0 plus 1, and this plus 1 again. Why? Because for the third time I am using my denomination 1. First I used it over here, second I use it over here, third I use it over here. I used it 3 times, that's why I am left with a 1 over here. Otherwise there was no way I could have reached this 1 if I wouldn't have used 3 ones over here, or if I wouldn't have made use of the 3 coins of one denomination. Now in the case of min coin 1, 0, what I would be doing? Again, I would be branching out. In one branch I would be making use of the element present at this index. So if I make use of that, then what would I be left with? I would be left with an amount of 0, because look, currently I have a 1 with me. If I just reduce the denomination of 1 from it, then what would I be left with? I would be left with 0. And if I do not include it, so what would I be left with? I would be left with min coin 1, 1. Now what does this problem specify? This problem specifies, look, that currently I am at index 1. Just tell me, what are the minimum number of ways? What are the minimum number of coins with which I can make 1 over here? So what does this problem specify? Min coin 1, 1. This states this thing. I have a 2 and a 3 as denomination. Just tell me, how can I make 1 out of it? Or what are the minimum number of coins needed to make 1 out of it? So what is this min coin 0, 0? This min coin 0, 0 states that I am sitting at index 0. Just tell me, starting from this index till the end of the array, what are the minimum number of coins to make amount of 0? It says this thing. I am sitting at index 0. Index 0. just tell me till the end of the array, how can I make an amount of 0 with it? Okay, you are given a denomination of something. Can you ever make an amount of 0 with it? No. So what are the minimum number of coins needed to make an amount of 0? It's 0. If you are nothing left with something, so how many coins do I need to make such amount? I would be making use of 0 coins again, because there is no sum left with me. Hence we hit this base case. So this 0 over here, this specifies that to make a leftover sum of 0 or leftover amount of 0, I just need to have 0 coins with me, or the minimum number of coins needed to make a leftover sum of 0 is 0. Hence I would be returning 0 over here. So this would be 0 plus 1. So we have a 1 over here. Just remind that, or just keep in mind that thing. What is this min coin 1 1? Again, min coin 1 1 says that I am sitting at index 1. Just tell me till the end of the array starting from this index, what are the minimum number of coins with which I can make 1, or this thing I think I have told you earlier as well. Yes, how can I make a 1 out of these two denominations? So what I would be doing, again I would be branching out. I would be branching if I consider this the element present at this index. So what I would be doing, I would be subtracting that element from this one. So what would I be left with? I would be left with min coin minus 1 1 plus 1. And if I do not include it, what would I be left with? I would be left with min coin 1 2. Now what is this min coin minus 1 1? Okay, this says starting from index 1, which is 2 again, till the end of the array. So if I start from index 1 till the end of the array, so what are the denominations which I have? I have 2 and 3. Just tell me what are the minimum number of coins which are needed to make a amount of minus 1. So it is this thing, and you have infinite supply of all these coins. Just tell me, can you ever create a negative integer by summing up some positive integers? No. So even if you have infinite supply of all these items, of all these denominations, but then also you can never make minus 1 out of it. If you need something in negative as an output, so you need to have some kind of negative denominations with you, but that is not even possible. You cannot have some kind of negative denominations with you. Hence, even if you have infinite supply of these denominations, I can never make minus 1 over here. Hence I would be returning minus 1, and this is that base case. What does this int max minus 1 states? It states that if you are left with any sum or any amount which is less than 0, so you need to have infinite amount of coins to just make that sum possible. Or what does this return? This returns that the minimum number of coins which I need to make this amount from these denominations is infinite. That's what I did over here. I would be returning int max minus 1, and you need to see that why am I returning int max minus 1 over here. Look, if I would have returned int max over here, then what would it be? It would be 2 to the power 31. So if I just add a 1 to it, so I would be overflowing my integer. Hence it would lead to a runtime error. So you can do int max minus 1, int max minus 2, int max minus 3. Just keep in mind that it shouldn't overflow. Your integer shouldn't overflow over here. Now coming on to this min coin 1 3, what does this problem states? This problem states that I am present at index 3. Now starting from this index till end of the array, just tell me what are the minimum number of coins with which I can make 1 over here. So this subproblem states this thing. This subproblem states this thing. What is this index 3? Do I have even index 3 over here? No, I am out of bound. So I have no denominations left with me now. So hence I am left with no denominations, but I need to make an amount of 1. So even if I have infinite supply of no denomination with me, but I can never make 1 out of it. So this is this base case. So if my current index is greater than equal to size of the array, then I need to return int max minus 1 over here. So what does this problem say? That I am left with no coin, but I still need to make an amount from that. So even if I have supply of infinite number of coins, then also I cannot do it. Hence I would be returning infinite over here, and by infinite I mean to say int max. Now what would here be? It would be int max minus 1 plus 1. So this is int max. This would be again returning int max. So min of int max and int max would be int max again. So what does int max specify over here? The answer to min coin 1 2 is int max. Or what was this sub problem? It was this thing, that I am currently at index 2. Just tell me, starting from this index till the end of the array, how can I make 1 out of it? How can I make 1 out of it? So my answer to this is int max. So what does this int max specify? This int max specifies that with these number of denominations, I need to have infinite number of denominations, but then also I cannot make 1 out of it. Again, can you ever make 1 out of these denominations? No, because again, what are the denominations which you, what is the amount which you can make out of this 2 and 3? The least amount which you can make out of this 2 and 3 is 2, because that would be a single denomination of 2, single coin of 2. So can you ever make 1 out of it? No. So this int max states the same thing, that even if you have int max or infinite supply of these denominations, but then also you cannot make 1 out of it. Hence I would be returning int max over here. What about this min coin minus 1 1? Again, I need to make an amount of minus 1, whereas I am currently sitting at index 1. So what was this sub problem? It said that I am currently sitting at index 1. Just tell me, starting from this index to end of the array, what are the minimum number of coins to make minus 1? So it would be again int max. And what does this int max specify? This int max specifies that even if I have infinite supply of these coins, then also I cannot create minus 1 out of it. And hence int max would be the answer to this as well. So min of int max would be int max. So what is the answer to min coin 1 1? It is int max. And what was this sub problem? It says that I am currently sitting at index 1 or 2. So starting from this index till end of the array, starting from this index till end of the array, how can I make 1 out of it? Again, you cannot make 1 out of it. So the answer is int max. So we have an answer of min coin 1 1 as int max again. So, and what was the answer to this case? It was 1, because this case returned 0 and I added 1 over here. I think you would be knowing why I added over 1, why I added 1 over here. It was because I made use of a coin. This is the branch where I was using all my coins, and this was the branch where I was not using any of the coins. So min of 1 and int max would be 1. So the answer to min coin 10 is 1. And what does min coin 10 states? Min coin 10 states that I am currently sitting at index 0 or at this 1. So starting from this index till end of the array, starting from this index till end of the array, what are the minimum number of coins to make 1? So its answer is 1, because you surely can make an amount of 1 with the help of these denominations by picking just single coin of 1, and hence min coin 10 has an answer of 1, and that 1 signifies the minimum number of coins with which you can make 1 starting from index 0. I would be again adding 1 to it, so this would be 2. Okay, let's just break min coin 2 1 as well. Now what does min coin 2 1 says? Min coin 2 1 says that I am present at index 1. So starting from this index till end of the array, just tell me what are the minimum number of coins needed to make an amount of 2. So it states this thing. So if you are left with an amount of 2 and you have these two denominations, so what are the minimum number of coins which I should have? So I would be breaking down. I would be again using one branch for including the element, and second branch I wouldn't be including the element. So if I include the element present at index 1, so what would I be doing? I would be left with amount of 0 then. Look, what is present at index 1? 2 is present at index 1. So if I just make use of this denomination, so what is the leftover amount I have? I have a leftover amount of 2. If I make use of this denomination, what would I be left with? The leftover amount would be again 0. And I would be adding 1 to it again. Why 1? Why adding 1? Because I made a use of this denomination over here. I made a use of this coin. What does this subproblem state? Min coin 0 1. This states that starting from index 1 till end of the array, starting from index 1 till end of the array, means starting from index 1 till end of the array, what are the minimum number of coins with which I can make a 0? I am talking about this subproblem. So how can you make an amount of 0 from these coins? Again, for making an amount of 0, you need not need even a single coin. So the minimum number of coins to make amount of 0 is 0. Hence I would be returning 0 over here. And what does this 0 signify? This 0 signifies that for making an amount of 0, I need 0 coins. Even if I have infinite supply of each and every denomination with me, but if the amount itself is 0, then how many coins do I need? Minimum number of coins. That would be always 0. So this 0 plus 1. So the answer to this thing is 1 over here. Again, keep in mind that we would be recursing for min coin 22. What does min coin 22 says? Min coin 22 says that I am currently sitting at index 2. I am currently sitting at index 2. So starting from this index till end of the array. Starting from this index till end of the array, what are the minimum number of coins with which I can make 2? Okay, so we will just include once this denomination and we won't be including that denomination. So if we include it, then what are we left with? We are left with min coin minus 1, 2. And what do you mean by this minus 1? Why this minus 1 happened? Look, what amount I was left with? I was left with an amount of 2. So if I make use of this denomination present at index 2, so what is the leftover amount then? I would be subtracting this denomination from my leftover amount of 2. So if I subtract 3 from 2, what would I be left with? I would be left with minus 1. So what does this subproblem say? This subproblem says I am sitting currently at index 2. I am currently sitting at index 2. Tell me, what are the minimum number of coins with which I can make minus 1 out of it? Again, we will hit our base case, that is this base case. My leftover sum or leftover amount is less than equal to 0. Sorry, this would be less than 0. So what do I do? In this case, I would be again returning int max minus 1. What about this min coin 2 3? Again, I would be returning int max because there is no index as 3. I have gone already out of bound. So if I am, what does this subproblem actually mean? This subproblem means this thing, that I am left with no coin, but I still have an amount 2 to be made out of it. So even if I have supply of infinite for no coins, then also I cannot make 2 out of it. Hence I will be returning int max minus 1 or int max. So min of int max and int max, it would be int max. So what is the answer to this subproblem? Min coin 2 2, it would be again int max. And what was my min coin 2 2? Min coin 2 2 was this thing, that if I have a denomination of 3, what are the minimum number of coins I need to make for an amount of 2? Again, it would be infinite number of coins, because even if I have infinite number of 3s with me, then also I cannot make 2 out of it. So answer to this subproblem is int max. What was answer to this subproblem? It was 1. So min of 1 and int max would be 1. So the answer to min coin 2 1 is 1. Okay. So answer to min coin 2 1 is 1 over here. And what does this 1 signify? This 1 signifies that starting from index 1 till the end of array, what are the minimum number of coins to make an amount of 2? It would be 1. So starting from index 1 till the end of the array, what are the minimum number of coins needed to make 1? Oh, to make 2. That would be 1 again, because I already have a 2 over here. If I just pick this 2, I am done with my amount. Hence, that 1, the answer to this problem is 1, and that 1 signifies this thing, that the minimum number of coins to make 2 with the help of these denominations. And what was the answer to this thing? It was 2 again. So min of 2 and 1 is again 1. So the answer to this min of 2 0 would be 1 over here. 1 plus 1 2. I need to recurse for this thing, but due to my space constraint I couldn't do it. But I really ask you to just start recursing for all these subproblems. You will need to check the overlapping subproblems, and you will need to know how the optimal substructure is made. So whatever it may be, but I couldn't recurse the whole recursive tree over here, but I think you would have got an idea how I recursed this a part of my complete recursive tree. So the above this recursive tree gives me two ways to make this amount. One is 1111, and how did I get this 1111? I was initially given an amount of 4, I made use of 1, I was left with 3. Again I made use of 1, I was left with 2. Again I made use of 1, I was left with 1. I again made use of 1, I was left with 0. So this recursive path shows that I made use of 4 ones. And how would I achieve 112? I made a use of 1, I was left with 3. Again I made a use of 1, I was left with 2. I didn't make use of 1. Then I started making use of 2, because look, I made a use of 1, I was remaining with 3. I again made a use of 1, I was having 2 as my leftover amount. Then I didn't make use of 1. If I would have made use of 1, then I would have left with 1 over here again, but no, I just sent all of my leftover sum. So this thing means that I didn't make use of 1. So if I just started recursing for this one, so what does this subproblem say? This subproblem says starting from this index 2 till end of the array, what are the minimum number of coins I need to make 2 over here? So that would be picking a 1, 2, and hence this was the 2 over here. That's why I have a 0 over here. Look, I was leftover amount with 2. I just made use of the denomination present at index 1. And what was present at index 1? It was 2 again. So 2 minus 2 is 0. So I just made a use of 1. I just made a use of 1. Then I made a use of 2 over here. And hence I got this. So this path, this is actually our 112. So the same way you would be recursing for other ways as well. So, and what were the other ways? The other ways were 1, 3 and 2, 2. If you just recurse for each and every subproblem or these remaining subproblems, then you will see that you will get a path for 1, 3 and 2, 2 as well. And that would be our minimum number of coins, which can be used to make an amount of 4. Now, what do we see over here? We need to check two properties, that do we have overlapping subproblems and do we have optimal substructure. Now, coming on to overlapping subproblems. Now, if you just open up this subproblem, min coin of 3 and 1. So what does this problem say? That currently I am sitting at index 1. Just tell me, starting from this index, means starting from this index till end of the array, what are the minimum number of coins needed to make 3? That's what now. What are the minimum number of coins which I need to make an amount of 3? So what would I be recursing? The one case would be when I make use of the index present at when I make use of the denomination present at index 1, and in the other branch I wouldn't be making use of that one, or the denomination present at index 1. So if I do not make use of denomination present at index 1, so what would I be branching for? I would be branching for min coin 3, 2. And if I make use of it, then I would be branching for min coin 1, 1. But again, I would be adding 1 to it. Why I added 1? Because I made use of this index 2. Oh, this index 1. And the denomination of that on that index was 2. Hence, I would be subtracting this 2 from the leftover amount, and I would be left with only 1. Now, what is this subproblem? Min coin 1, 1. And what is this subproblem? Min coin 1, 1. So we can easily see that we do have overlapping subproblems. So our first property is fulfilled towards our DP solution. Now the second property is, does this problem have an optimal substructure or not? So we can easily see that it has an optimal substructure. And why can we see it? Because with the help of all these base cases, with the help of this recurrence relation, and with the help of all these subproblems, we can reduce a solution for our main problem. And that is an optimal substructure. So we do have optimal substructure, we do have overlapping subproblems. So we can surely say that this can be solved with the help of dynamic programming. So in the next lecture, we will be discussing the bottom-up approach to this solution and how do we build our DP table. And with the help of the tabulation method, we will see that how our polynomial time complexity is just reduced to, how is this exponential time complexity of this algorithm, of this recursive algorithm, is just reduced to a polynomial time algorithm. So till that, thank you.